Hi, hello. Okay, so I think we're recording. This video is going to be the solution for problem 3 of the first discussion section worksheet. Um, you should have already looked at the videos for problems 1 and 2. If not, I highly recommend you go at least look at 1 because in the first video, Sariel sort of goes over the explanation of what the questions on this worksheet are talking about, and I don't want to bore you by going through all of them again. So, but just quick recap. This week we're just asking you to prove some quote-unquote obvious claims about recursively defined string functions. What we mean by obvious is that they're pretty intuitive, they're pretty simple to understand, but we want to prove them formally because this is a theory class. And we're given these two definitions. One has to do with the size of a string, and then the other has to do with string concatenation. So you should be familiar with those. Pro tip: it's helpful to just write out next to, like, over here or something, like next to all these definitions and lemmas, what the notation is actually saying, because it's pretty easy to just get lost while staring at all of the symbols and stuff. Anyways, so yeah, question 1, just here we proved that a string and its reversal are the same size. That's pretty obvious because reversing a string isn't going to add or remove any characters. Problem 2 is, or the question 2 is a claim that is not as obvious, but it's pretty helpful. And I only mention this because the hint for question 3, which is what we will be doing, is to use 2 to prove 3. So you could have gone and seen what question 2, or how question 2 is proved, just to give a concrete example of what question 2 is about. It's basically saying if I had, say I had the words cat concatenated with dog, right? So that's cat dog, and if I wanted the reversal of this, well, that would simply just be godtac. Is that right? Just wanted to make sure. Okay, yeah. So that's what that would be. But a way we can break this down recursively is by observing that this is the same thing as reversing dog itself and putting it before the reversal of cat, right? Which gives us exactly this. So that's cool, that's nice, and we're going to be using this and maybe some of these lemmas. Like I said before, it's helpful to write in English what these three things do and what they mean, so that when we go to formalizing proofs, you just have an easier time. So the proof I will be writing and how I'm writing it is different than what the solution key says. You should look at the solutions, obviously. But I'm going to be going through it a bit more pedantically, sort of from like notation you'd see in 173, because I know we all took 173. So without further ado, let's get right into it. So I'm going to rewrite this claim over here. So we want to prove that. So the claim we're interested in is prove that the reversal of a word is just the word, right? Simple enough. I hope we're all convinced that this is true. Anyways, okay, triple checking that that is the correct claim because it would be super bad if it wasn't. Okay, so I want to prove this. We watched the other two videos, or at the very least we looked at the solutions for the first two questions. And in general, anytime you see recursion, you should think, hey, a proof by induction seems like a pretty great strategy. When we learned induction, we always learned that it was very important to define, the induction variable. And again, I'm being super pedantic, so I'm going to write the induction variable. I'm going to call it S, where S is the size, denotes the size of the word, right? And we do this partly because, again, questions 1 and 2 induct on the size of the world, also, word, not world. Also because we're given this definition, and it would make sense because we have clearly defined steps here, and so why not, right? I'm also going to go ahead and pedantically define what exactly we're proving at each step of the induction. So I'm going to say, let P of S denote the following. And the following is all words W such that the size of the word W is equal to S, or I'm going to say for all. This claim, this guy, is true. So, but again, for words of this particular size. And again, this is me being very pedantic, but why not, right? And so great, now we have this P of S, so I don't have to keep writing this over and over again. Note that, again, this is for a fixed S, right? If this wasn't for a fixed S, then I'd be assuming the thing I want to prove. We don't want to do that, which means that this our original claim, I can rewrite it in more notation as for all possible word length sizes, right? So for all S in the natural numbers, P of S is true. You should convince yourself why this statement is the exact same as this statement, though we did forget to, quantify for all W words. Great. Okay. So now, it's pretty standard induction procedure. So first I do my base case. Great, good. Okay. So what my base case is S equals 0, right? And the only word we know of size 0 is our friend the empty word. So then I'd write the only W such that the size of W equals 0 is the empty set, or the empty string. Also, I'm realizing now that I'm calling strings words, but I hope that doesn't throw anyone off. So for the empty string, we want to show that P of 0 holds, i.e., we want to show that whatever this word is reversed and reversed again is just the original word. So then we say, hey, look, when this is the case, in this scenario, the empty string reversed is just the empty string, right? And so that means that if I reverse this reversal, we could play a game with all the times I'm going to say reversal in this video. That's just the empty string reversed again, which is the empty string. And so we can think of this as the left-hand side of the claim. And then the right-hand side, W is simply equal to the empty string. So then I say, hey, left-hand side equals right-hand side. Then we're good. Again, I'm being very pedantic. It suffices to just say, look, the empty string reversed 2 times is just the empty string. And that's fine and dandy, and we can move on. Okay. So, anyways, so next step, induction hypothesis. Because we've so cleverly, not cleverly, but like ardently defined what P of S is, I can say, hey, fix some K in the natural numbers, right? And assume that P of S holds for when S equals 0 all the way up to K, okay? So again, because we wrote this P of S, this is all the induction hypothesis looks like. If I didn't define a P of S, I'd just say, hey, for all words up until this certain fixed size, the claim I'm trying to prove being that the reversal of the word is just the original word, that holds true. Okay. And so that means our induction step is I want to show that the claim holds true for strings of size P, or strings of size K plus 1, right? So just to remind us in this block of my iPad screen what we're trying to prove, I want to show that for all words W such that W is at most size, it's equal. I said equal. Yeah, I said equal. Okay. Size k plus 1. The word reversed is equal to the word, right? That's what I want to show. So I say, okay, let W be such that be some k plus 1 sized word, right? Okay. And so then I say I should probably think about W reversed, right? Okay, cool. And we're going to take a moment here before we proceed to sort of like map out what we want to do. I had mentioned before, I just tried scrolling on my laptop instead of my iPad. Okay, so I said before, and this hint says that we need 2 to prove 3, but you may find it easier to solve 3 first. Okay, so it says I need 2 to prove 3. Great. Might as well. And we probably also need the definition of reversal. That seems just smart. So I'm going to call that 1, and I'm going to call the claim from 2, 2. Okay? And so let's go back to what we were doing, right? So first we should deal with the inner reversal, right? So we should probably reference the definition, right? And so W reversed, when W is the empty string, we actually used 1 in our base case, right? So 1, let me just, 1 should be cited here, okay? For our induction step, we are going to be using the recursive definition. We should probably also say that, hey, we're in this case, right? Because W is of size k plus 1, and k is at least 0. So k plus 1 is going to be at least 1. So we can write our word as a character or a symbol a and some string x. So let's do that first. So that means that, hey, W is going to be equal to a times some x, where a is a symbol and x is a string or a word of size k. Okay, great. And so this is the same as ax, my bad. Ax r, right? R. Okay. Then we use our definition of 1, which tells us that xr or axr reversed is xr concatenated to a. Okay. So then I just, again, plugging and chugging the definition, and that gives me this reversed. Okay. So then we say, or not we think, where do we go from here? And what are the other tools in our toolkit to use? 2 seems like it's helpful. And it seems like we're in a situation where we can use 2, because 2, just like visually, right? 2 is talking about 2 things concatenated together, reversed. Okay? And here, in what we're given, we have 2 things that are concatenated together. Yeah, they're not necessarily words, but okay, Siri, chill. I hope my audio didn't cut out. We have 2 things concatenated together, reversed. So might as well try and use this, right? So going off of 2, okay, first of all, we cite 1 here. Here, no. Now we're going to cite 2, claim 2. I'm not writing out as words, but you should always remember to cite and explain what you're doing as you're going. Claim 2 tells us that this is simply a reversed, and remember, a is a symbol. A reversed concatenated to x reversed. Okay? So now we have 2 things. A reversed, a single symbol or a single character reversed is just itself, right? So because of that, we just get this. So that's one step we're doing. Okay. Now, we've gotten this far. We haven't used our induction hypothesis. We probably should use our induction hypothesis because we're doing an induction and that's just helpful. And like I mentioned before, X is a string of size K. More importantly, X is a string of size less than K plus 1, which means it falls into the realm of what our induction hypothesis assumes. So then, so I'm going to write here first that A is a symbol. So AR is just A. And then this next step is going to be using the induction hypothesis. What do I know about this? Well, our induction hypothesis says the reversal of a word is just itself. So that tells us that this is simply A concatenated with X, right? Because that's how this is specifically where we use the induction hypothesis. And now we say, look, this is precisely what we define W to be. So this just gives us W. And so what we've shown is that it is indeed the case that for this K plus 1 sized word, the reversal of its reversal is itself. And we're pretty happy because that's what we wanted to show. And then we can throw a by induction. I'm going to check mark that. By induction, we've proven the original claim. Cool. So, a couple closing remarks, I suppose. Like I said before, this was incredibly pedantic, but we're in 374, not 173. So you can be a little bit more slick about how you prove these things. Look at the answer key that will be posted. I think, though, when you do practice, it's very easy to assume, oh, I know how to prove this because it is so obvious. But if you don't know how to formalize it, fall back on like these old tricks you've seen in 173 and you've seen in other classes because it's super straightforward and yeah, it's a bit tedious to write, but like at least you write a proof. We don't want to, be so slick and so lax with our attention to detail that we just write a proof sketch, or worse, write something that's just logically incorrect, right? Anyways, I don't know how to like end these things off. Like, be sure to like leave a comment, subscribe, press the bell. No, but in all seriousness, please try and attend discussion sections, come to office hours if you have questions. I promise you the TAs aren't scary. Post on Piazza. I hope you all are doing well. Here's a smiley face. I don't know what I'm doing. Okay. Great. Alrighty. Goodbye.